Do you want to know what fundamental skills and knowledge an actual electrical engineer needs in their day-to-day job? Well, stick around because in this video series, I'm going over all of the electrical engineering material that I learned in my college courses and how it relates to my job as an electrical engineer. This video series is going to be very to the point. I'm not going to give you a bunch of extraneous information or stuff that I don't think is important for your job if you wanted to work as an electrical engineer. And I'm using my experiences as an actual electrical engineer to kind of help inform those decisions about what I think is important to teach and what things I think we can kind of skip, what topics I think we can skip over. So in today's video specifically, we're going to be going over, I have a list of notes prepared, and then we're also going to take a look at some circuit simulations. So this is going to be basically the first thing you ever learn if you want to start becoming an electrical engineer. So we'll be talking about like voltage, current, power, DC versus AC, stuff like that. Before we go any further though, please go ahead and drop a like on the video for me. It helps my channel out a ton. And subscribe if you'd like to stay up to date with any future videos. Now with that out of the way, let's just jump right into it. Like I mentioned, this first chapter, this first section, first video is going to be talking about some of the most basic fundamental concepts related to electrical engineering. So we're going to be answering some questions like, what is voltage? What is current? What is power? There is a textbook that I am kind of utilizing and following along with. So if you want to kind of read up or follow along on your own with me, the textbook is Fundamentals of Electric Circuits, 7th edition by Charles Alexander and Matthew Sadiku, I think is how you pronounce his name. So that's just the textbook that I'm using to follow along. I mean, most basic, intro level electrical engineering textbooks cover the same topics. I had another one I looked at, covers mostly the same information. And I have my own little notes that I've added in here and stuff like that. So yeah, let's just start out with the first topic, 1.3, charge and current. So the concept of charge is super important for understanding electrical circuits. So you might, if you've taken any like high school chemistry courses or maybe even some intro gen chem courses, you understand that maybe the first time you ever hear about charge is pertaining to like protons and electrons. So like protons have a positive charge, electrons have a negative charge. And this actually relates to electrical engineering and electricity because charge is an electrical property of matter, i.e. an electrical property of atoms. And in electrical engineering, charge is measured in coulombs with the little unit C right here in parentheses. And then I even mentioned, like I said, protons have a positive charge, electrons have a negative charge. One important property or feature of charge is that it's actually mobile. It can flow. And by flow, we mean it can transition from atom to atom. And this is like a fundamental concept pertaining to chemistry as well, is when you have like chemical bonds are formed by the exchange and sharing of electrons. And if you remember, there's some specific elements that actually exchange and share electrons particularly well. And we'll get into that stuff later a little bit. But, spoiler alert, we're talking about like metals like copper and aluminum and gold and zinc and stuff like that. And some other elements have some unique properties that we utilize in electrical engineering as well. But that's all you really need to know is charge is mobile, it can flow. And electric current, we can actually measure the rate of which this charge is flowing, and that's what is referred to as electric current, right? So the actual definition, electric current is the flow of charges, specifically electrons, and it is measured in amperes or with the unit A. Here's a little equation here. You have I. I is also a way to denote current. So A is the abbreviation for amperes, but I, for whatever reason, I don't remember why current is referred to as I. So there you have it. So current is proportional to change in charge over change in time. So this is a little calculus term. It's really not that important to know the calculus part of this. Just understand that it's just the rate of flow of charge. There are two main types of current that we utilize in electrical engineering. One is called direct current or DC. The other is alternating current or AC. So a pop culture reference to this might be the band AC/DC. At least I think they're related to that. I hope they are. They have like a lightning bolt in their logo, so I didn't embarrass myself and was wrong about that. Continuing on though, Direct current, or DC, flows only in one direction. And we'll talk about this. We'll demonstrate this in a little circuit simulation that I have at the end of the video. And so, yeah, DC is only flows in one direction. It can be constant or time varying, meaning it can be like you can change the value of it. So it can go from like 1 amp to 2 amps, 1 amp to 0 amps, but it only flows in one direction. So it will never go from like 1 amp to -1 amps if it's DC. Alternating current, or AC, on the other hand, does change direction with respect to time. So this can be changing, this can go from like 1 amp to -1 amp and back to 1 amp and back to -1 amp, right? So it can be some type of oscillatory behavior or something like that. And here we have a couple graphs, and then I actually pulled some actual images off the Google to kind of show some real life examples of this. So let's first talk about the graphs here. So this is just a graph of DC. It's really not that special. It literally is a straight line across the screen because it's constant, right? This represents some type of DC source. And like I said, it's just it's a flat line because it's not changing over time. This one doesn't really show. It could be turning on or off or increasing or decreasing, but it will never go below 0. And a good example of DC would be a battery. So if you plug a battery into a circuit, current is only able to flow one way, and that is pertaining to the terminals of the battery. So it's not actually switching in real time, and so any circuits that utilize a battery are DC circuits. Then next up we have a graph of AC, and you can see this was like a sinusoidal graph right here, and you can see it sort of oscillates. It's in this region of the graph we have the current is negative, and this region of the graph it's positive, and it even touches down and hits 0 occasionally, right? So it's doing real wavy like shapes, you know. And a good example of this is actually your wall outlet. Now this is an American wall outlet, so if you're not in America, you know what a wall outlet still looks like. If you plug it in, you're going to get some amount of AC voltage out, and it also depends on where you live in the world. This could be as low as like 85 volts all the way up to like 265 volts AC. And so it's going to look like this coming out of the wall. However, the amplitude will be a little bit different depending on where you live in the world. So here are just some good examples of AC and DC voltage sources, which I think is a great segue into talking about, well, so what is voltage? What does that even mean? So the standard definition or concept for voltage is basically what it takes to move an electron in a conductor, right? So here we have voltage is a measure of the electromotive force. So if you kind of think back to physics, like it takes a force. If you say you want to push a couch across the room, it takes a force to do that. So if you want to push an electron across a wire, it also takes a force to do that. And this force is known as the electromotive force, or EMF for short. You will, in industry, you'll never really run into electromotive force, or the abbreviation EMF will stand for a lot of other things. So don't get used to referring to voltage as the electromotive force. Just refer to it as voltage or volts. And that's fine too, because like I said, it's only a measure of the electromotive force. So it's like you might get something like a 9-volt battery, a 12-volt power supply. Those are some examples that you might see, some everyday examples, right? One important feature of voltage is that it is a differential measurement between 2 points. For example, measuring points A to B, sort of like in physics, if you remember that, like in order to measure velocity, you need a reference point, right? So if, like, if you remember the sheep on the train example, where from compared to someone else on the train, the sheep is only running like 10 meters a second, but if you're off the train, you have to sum both the train speed and the sheep speed. Or I know this is probably an ambiguous example, but something it's kind of like that. So and you need a reference point always when you're measuring voltage. There's no absolute measurement for voltage. And so in electrical engineering, what we've typically done is there's sort of a universal reference point known as ground, and we'll talk more about that later. But just know for right now that in order to measure a voltage, you need a reference point. And so I have some little diagrams we'll talk about, but let's continue on with this portion. So in electrical engineering, voltage is almost always measured with respect to something called ground. Oh, look at that. I'm so ahead of myself. Ground is a universal reference point in all circuits that is supposed to have zero charge. We'll explore this topic more later on. Okay. So here in these diagrams, we just have a simple voltage measurement being taken. And so we have VAB, which is just V across points A and B. And then this was a generic like algebraic term that we have. And so right here, I just took another example that literally just has a number associated with it. So you might say you would say the voltage drop across A to B is 9 volts. And right here, so current always flows from a point of higher potential to a point of lower potential. Yeah, so the way you measure voltage is you refer to the voltage drop, quote unquote, right? So say we're trying to measure the voltage drop across A to B, you would measure the voltage at A minus the voltage at B. So looking down here, VAB equals VA minus VB. And so this is sort of an arbitrary denotation, but where we have the minus sign, we're just saying that's quote unquote 0 volts, and we're having the top is 9 volts. So that way we're just attributing also a directionality to the voltage. So hopefully this won't confuse you. I think it makes more sense when we look at examples later on. We just understand that whenever we're measuring the voltage drop across something, we're taking the positive one and subtracting it we're subtracting it by the negative one. So VAB right here is VA, the top, minus VB. And so in this case, if it's 9 volts, we have 9 volts up here, and we have 0 volts down here. Another important note to make here is that current will always flow from a point of higher potential to a point of lower potential. So if you've taken like thermodynamics, or I think I even learned about this maybe in middle school science, and I hope I get this right, it's heat transfer usually goes from hot to cold. So you kind of think of if heat is in terms of higher potential, like it's higher amounts of energy. If something's hot, it has a lot of kinetic energy, then it always transfers from higher kinetic energy to lower kinetic energy, which is something that's cold. And so that's basically how heat transfers. And voltage is current is a very similar thing. So it always flows from a point of higher potential to a point of lower potential. Okay, moving on. So now let's talk about power and energy. So the definition of power for electrical engineering purposes is the time rate of expending energy or absorbing energy measured in watts. So the equation for power is P equals VI, so that's voltage times current. So I have this little diagram down here again where we see the little arrow showing the directionality of current flowing from a point of higher potential to a point of lower potential, and it's flowing through this little circuit element. And in order to find out the amount of power that is being absorbed by this element right here, we would have to multiply the voltage drop across it times the amount of current flowing through it. So in this example right next to it, they actually give us some real numbers associated with voltage and current. For example, we have 3 amps and 4 volts. So if we want to figure out the amount of power that's being absorbed by this element, we have 3 amps times 4 volts equals 12 watts of power being dissipated or absorbed by the element R. And it's as simple as that. That's power. Next up, I think is a good segue to start talking about like a little bit more about this thing that we're seeing right here. So this is a circuit element known as a resistor. We'll talk about a whole bunch of other circuit elements, which are the basic building blocks of a circuit, right? So that's what the definition of a circuit element is. You have 2 major types of circuit elements. You have passive elements, which do not generate energy. Some examples are resistors, capacitors, inductors. And we'll talk about what capacitors, inductors, and resistors are later on in a different video. And then we also have active elements which generate energy. So we're talking about voltage sources, current sources, batteries, wall outlets. Those are all examples of active elements. There are 2 major kinds of sources, though. So one kind is independent sources, which are completely independent of other circuit elements. They always provide the specified voltage and or current. And we'll see this in some circuit diagrams and schematics that we see later on. And then dependent sources are controlled by another voltage or current. And so one example of this would be like a transistor or a MOSFET or an op amp. And don't worry if you don't know what any of these are. We'll talk about them later on as well. But just kind of have in your brain, okay, there's independent and dependent voltage sources. Okay, so now let's go ahead and take a look at some actual circuit diagrams that I have pulled up. So example 1-1 is going to be, let's just take a look at it here. So this example right here is an example of a DC circuit right here. So if you see right here, I have a 12 volt DC voltage supply. And then I have a circuit element known as a resistor. So this is the symbol for a resistor right here, with these little squiggly lines. And then right here is just some wires, right, connecting the elements together. You can kind of see, pay close attention. Notice how there is current kind of flowing through the circuit, and watch how the electrons are flowing. So we have going from a point of higher potential here down to a point of lower potential down here. So it's important to note, like I said, this is DC or direct current, so it's only flowing in one direction. And we'll take a look at an AC source in a second, so you'll see. But right now, yeah, all the charges are flowing in the same exact direction. So this thing up here right now, I'm just measuring the current flowing through, and we'll pull this up in a scope probe. So that's all this thing is at the top, is measuring the current that's flowing through this circuit right now and through this resistor. Oh yeah, so this resistor has a value of 500 ohms right now, and we'll worry about those details later, but that's what the number 500 means next to it. And then 24 milliamps is how much current is flowing through there. The other thing I have on this circuit, maybe that might look a little confusing, is this is just measuring the voltage drop across the resistor. So if you remember going back to this right here, measuring the voltage drop across a resistor, that's exactly what we're doing right here. And I can even like delete this part of it, so you can clearly see this is the part of the circuit, and that was just a measurement device. Another thing I want to pay attention to is, so I have two circuits right here, and the only difference right here is this ground right here. And that's just a notation in electrical engineering on the schematic that just denotes a point of the lowest, the reference potential that we're using, the ground that I was talking about. And it's just a way to show closure of the circuit. So in order to get current to flow, you need both ends of this battery or this voltage source to be connected to the circuit. So let's say I deleted that. See how current stops flowing? It's because the loop is open. It's not closed. So there's nowhere for this to flow. It needs to flow into a point of like lower potential, right? This is like really what it looks like. And so without any current to flow, or without the circuit closed, there's nowhere for the current to flow, right? So you need to close it in order to do that, right? And then we close it, then we see it starts flowing in, right? And then we can measure our voltages right here. Okay, and so the ground is just a universal reference point. It just helps make the circuits, simplifies them and makes them a little bit cleaner and easier to look at, right? Because imagine you get a whole bunch of components here and it just looks really complicated to have to connect them all back. Okay, so next up, let's take a look at an AC current source that I have created. So it's another very simple circuit. Okay, so the first thing I want you to take note of is the direction of the flow of charges. You see how they're kind of going back and forth and back and forth. It's almost like you have like one of those saws that people used to cut down trees with. They go, and that's a perfect saw sound. This is because if you look at this, I have the voltage being measured. You see how the voltage and the current values are both reversing and are actually going to the negative, right? So let's do a quick stop. So we can see here, we go all the way up to 120 volts, and then we go all the way down to negative 120 volts. Okay. So that just signifies the directionality of current flow, right? Which makes sense because at some points in the circuit, current's flowing forwards. At other points, it is flowing backwards. And so that's what AC looks like. The stuff that comes from your wall, has a sinusoidal shape to it. And So it's just important to understand, like, this is kind of what we're looking at when we look at an AC current source. And again, I have voltage and current being measured. And then similar to the last circuit, I just put some of the universal reference points known as ground in our circuit. That way you just kind of get used to looking at that. And so, yeah, and also this whole general thing we're looking at is referred to as like a schematic. So that's just shows all the electrical connections on the actual that the circuit actually makes up. And it's a model for like a real life. If you had these components in real life, then this is what on paper it would look like just as a representation. And I think that pretty much sums up everything I wanted to cover in this first video. Stay tuned for like the next videos I have coming out. We're going to start getting into more concepts like some circuit analysis tools like Ohm's law, Kirchhoff's current and voltage laws, and stuff like that. So thank you so much if you made it to the end of this video, and hopefully I will see you in the next one.